Hello everybody and thanks for tuning in. You are on the online course Easy Geosteering. In this course we explore the key geosteering aspects in simple words, following a clear and structured approach. We are currently in the second part of the course, BHA components, and in the previous video we covered MLWD surveys. And today we begin with the logging while drilling. Let's get started. So, main LWD methods used for geosteering are gamma ray, resistivity, and neutron density. We will discuss each type separately, but for now let's review some common characteristics shared by all logging methods. The first characteristic is the depth of investigation. It is the distance from tool's axis at which the tool receives half of the signal. The key point here is when we talk about logging, we cannot say we are measuring an exact point or a specific layer in the rock. Instead, each measurement represents a response from some volume of investigation around the tool, which contributes to the final value. Many factors affect depth of investigation, including tool design, sensor characteristics, and rock properties. And in our lesson, we will provide approximate values to give a general understanding. The second point is vertical resolution, the thickness of the thinnest layer that the tool can detect and measure. This parameter is generally inversely proportional to the depth of investigation. For example, the density log has high resolution, allowing it to detect thin sublayers, but its measurement is relatively shallow. In contrast, resistivity has lower resolution and struggles to differentiate thin sublayers, but it can measure deeper into the formation. The third point is environmental corrections, external factors that affect logging readings. Many factors come into play, such as mud parameters or bit size, and each LWD method has its own set of corrections. For example, potassium content in the mud can significantly increase gamma ray readings due to its natural radioactivity. If MLWD engineer doesn't apply necessary correction, the gamma ray value on the log will appear higher than the actual formation value. Okay, we have covered common characteristics of LWD methods, and now let's start with gamma ray logging. Gamma ray measures the natural radioactivity of rocks. The word natural is critical because some LWD methods also measure gamma ray, but use artificial sources. Three common elements, potassium, uranium, and thorium, are naturally radioactive and present in rocks. Due to mineral composition and sedimentation processes, these elements are mostly found in shale and clay formations rather than in sandstone. This means gamma ray can be used for lithology identification and reservoir characterization. If we speak about the depth of investigation, we can say it's approximately 40 centimeters. Now let's take a look at the behavior of the gamma ray curve in a typical terrigenous formation, which here is represented by shale, sandstone with gas, oil and water, and also carbonate and coal sublayers. First, pay attention to the blue horizontal line. This is a reference value of 60 API, and it serves as a conditional threshold. Values above 60 indicate shale, while values below 60 suggest a potential reservoir. Reference values for each logging method are determined by a petrophysicist and should be provided in the geological project for a specific well. Of course, it's a pretty common situation when reference values are unavailable. In such cases, interpretation in real time becomes more challenging for us, because a specific gamma ray level, for example exactly 60 API, could indicate a pay zone in one oil field but represent a non-reservoir in another. Okay, in the shale formation there is a high level of gamma ray due to high content of potassium, uranium and thorium. Then, as we enter the sandstone, the gamma ray value drops. As we can see, there are no significant differences between gas, oil and water, meaning we cannot detect fluid contacts and saturation using the gamma ray curve alone. Then we encounter hard sublayers that contain even fewer radioactive elements than sandstone, leading to a lower gamma ray level. And the same pattern appears in coal sublayers. Coal often has a lower gamma ray than carbonate sandstone, but without additional LWD methods, we cannot definitely distinguish between them. Alright, we outlined shared characteristics of LWD logging and covered gamma ray. Hope you like this video. Don't forget, you can enhance your practical skills with the private lessons. We use drilling simulators in StarSteer to immerse you into a realistic scenario as a true geosteering engineer. So stay tuned and give this video a thumbs up. In the next lesson, we will continue with resistivity logging. See you then. Bye-bye.